Okay. So somebody remind me, please, what Mendel's observations were that he based his laws off of. Yeah, Carrie.
Some traits mask other traits for the same character.
Yeah, so that observation, another way to state that is basically some traits are dominant, whereas other traits for the same character are recessive. Okay? And so that is absolutely one observation that Mendel made. Trinity, and then Lydia.
Oh.
Trinity, what is another observation?
Some individuals are true breeding for their.
Yeah, and so some individuals are true breeding, and this is especially important for individuals that are showing the dominant trait. Because again, we know some traits mask other traits, that is, some traits are dominant to the recessive trait. Some individuals that have that dominant trait, they'll produce offspring that have the recessive trait. They are not true breeders. But some of them are true breeders, and he used these data to basically indicate that every individual has 2 copies for every character. 2 copies of it. If they have the same copy at both of those, they are true breeders. If they have one of each, they are not true breeders. Lydia.
Some individuals are not.
Yeah! So the other side of that observation coin, some individuals are true breeders, some individuals are not true breeders, and again, the individuals that are not true breeders, they are heterozygous. They have 2 different versions of that character. Good, there's one more observation. Mr. Rick.
Recessive traits disappear when crossed with true breeding dominant individuals, but reappear in later generations.
Yeah, they don't blend out. These recessive traits do not blend out. Instead, they disappear completely when you cross an individual with that recessive phenotype with an individual with a true breeding dominant individual, but they reappear in the next generation. Carrie.
So is that observation similar to the first observation that some traits mask other traits?
Yes it is, but it's very specific in that even though it's masked, it's not gone, okay. Right? Because that first observation is just like, okay, we can mask this with another trait for the same character. But that second observation tells us even though you masked it and it may disappear in that individual, it's not gone. That information is still there. And this is especially important for genetic illnesses with a recessive inheritance pattern. Because you may have that genetic illness, but that doesn't mean that you're going to pass it on to your offspring, but that still that marker is there somewhere. Okay? It's a really important observation to keep in mind. Okay, what do we call a cross between 2 heterozygous individuals that are heterozygous at a single locus, at a single gene? What is the root for 1? Mono. And what is another way of saying heterozygous individual? Hybrid. So a monohybrid cross is a cross between 2 heterozygous individuals for a single character. Now, one of Mendel's laws is called the law of independent assortment. And somebody remind me what that law says. Trinity.
The separation of copies at one gene does not influence the separation at a second gene.
Yeah, which means that if you've got 2 different characters, you can treat them as 2 separate monohybrid crosses. Because the way one separates does not influence the way a second gene separates. That is, the law of segregation works for both genes. Okay? It's pretty good, right?
Can you say that again?
Yeah. So the whole thing?
Well, the character part. Like,
oh, yeah. So, the law of segregation works for both those characters individually. Okay, so if you've got 2 characters that you're looking at, the example we used was plant height and seed color. Okay, the way the 2 copies of the gene for seed color segregate in gametes does not influence the way the 2 copies of the height gene segregate during gamete formation. Okay, which means we can do what I showed you how to do at the very end of class on Thursday. If you're going to do a dihybrid cross, rather than building our big old Punnett square, we can just use algebra.
That was really cool.
Yeah, right? And so we know the phenotypic ratios of a monohybrid cross are what? What are the 3 to 1? 3, well, the monohybrid. Okay, shh. Okay, let's say, listen, I'm going to give you a character that really means nothing. Okay? So let's say we've got this character here, and we're going to use A to represent the particular traits for that character. Okay, so we have two different traits. We have the dominant trait for A, we have the recessive trait for A. Okay? And let's say we have a second character, and it's called the B character, and capital B is the dominant trait for that character, and what's lowercase b? It's a recessive trait. And let's just say for fun, right, for fun here, because we're all in the game of making science fun, we've got a third character that is the C character, and capital C is the dominant trait for that character, and lowercase c is the recessive trait for that character. And now let's get really crazy here.
Oh my gosh.
And we've got the D character. Now, if you were to do a monohybrid cross of two individuals that are capital A, lowercase a, what would the phenotypic ratios be?
Wait, can you say that again?
If you were to do a monohybrid cross of two individuals that had this genotype here, what would the phenotypic ratios be? There would be 3 individuals that are showing that dominant trait for every 1 individual showing the recessive trait.
Why is that?
Because let's do that right here. This is why it is. Let's say we cross a female that has this genotype with a male that has that genotype. This female can make 2 different gametes. She can make a gamete that has the capital A, and she can make a gamete that has the lowercase a. Right? Do you agree?
Yes.
This male, same. He can make a gamete that has the capital A, and he can make a gamete that has the lowercase a. So now when we do a cross of these 2 individuals, we will build a Punnett square where each individual can make 2 different types of gametes, right? If this sperm fertilizes this ovum, you get an individual that is homozygous dominant.
Say A squared.
You could say A squared, yeah, if you want, or capital A, either way. But it's, yeah, either way works. And then this would be capital A, lowercase a, this would be capital A, lowercase a, and this would be lowercase a, lowercase a. Okay? And so, what would this individual's phenotype be? What trait would you see? Capital A. What trait would you see here? Capital A. What trait would you see here? Capital A. So we get 3 capital A for every 1 lowercase a. Right? So, for this one, our phenotypic ratios will be 3 capital A for every 1 lowercase a. So if you produce 400 offspring, statistically speaking, 300 of them, or close to 300 of them, should have the capital A trait, and about 100 of them should have the lowercase a trait, right? That's also going to be true for a monohybrid cross of these individuals.
And every individual.
And a monohybrid cross of these individuals. And a monohybrid cross of these individuals. And if you're like, okay, I'm going to do a tetrahybrid cross, you could set up the most ridiculous Punnett square ever, right? Or you could just multiply all of these, what would we call these?
Binomials?
What's that? Binomials. Love it. We could just multiply all of these binomials together. Okay, if we multiply 3a times 3 lowercase a by 3 capital B times 1 lowercase b, and we FOIL these, we're going to get 9 capital A, capital B, yes?
Yes.
And then we're going to get 3, then we got to do outside, so 3 capital A, lowercase b, and then 3 lowercase a, capital B, and then 1 lowercase a, lowercase b, right?
Yes.
Yeah.
Yeah?
You don't
And
have
we're-
to get in the middle one every time.
And we're like, this is so cool. So our phenotypic ratios for a dihybrid cross are 9 to 3 to 3 to 1.
That's so cool.
And it doesn't really matter which way you present these. But so 9 out of every 16 offspring should have both dominant traits. 3 out of every 16 offspring should have the dominant A but the recessive B. Super cool. And then we could do the same thing. We could do the very same thing for our 3C and 1 little c, and then multiply that by our 3D and our 1 little d. Okay? Right?
Yeah.
And then we get 9 capital C capital D, and we get 3 capital C lowercase d, and we get 3 lowercase c capital D, and we get 1 lowercase c lowercase d. Right? And we're like, that's so cool, but we're doing a tetrahybrid cross, not 2 dihybrid crosses. And now what we do is we multiply these 2 tetranomials together.
81 ABCD.
Big words there.
And it's gonna
Just
be
call it polynomial after.
it's gonna be huge. It's going to be huge.
I just said that.
You know, I gotta tell you this. And then I'll share this link with my father. So my dad has always like really accentuated words with a silent H. He's loved them. I mean, he just loved
Like in
them.
Spanish?
I don't know what. No,
My
just
dad says you.
like our. You know, ours got that silent H. Like he just loves it. I don't know what it is. But ever since Donald Trump became president, every word in English that begins with the letter H, my dad turns into a silent H. Like Donald Trump. Like
house.
huge,
My dad's
human,
Ow.
ouse. I mean, he's really taken on this identity of the silent
No,
H.
my
So.
dad actually does that.
Almost.
Okay. So now, if we're going to multiply these 2 polynomials together, we've got to take this 9 CD and distribute it all the way across here,
This is a
right?
lot.
And then we got to take this 3 CD and distribute it all the way. It is a lot, but you know what it sure beats? Doing a Punnett square that would have 256 squares. It would beat it, but we're not going to do it anyways. I just want you to know you could do it this way.
It would have to.
And everybody loves this part of algebra too, right? Where you start multiplying complex polynomials.
Your dad is
The best
my dad.
Now, the beauty of this is Siri or Google, the Google Assistant, maybe even Alexa, would do this pretty quickly.
What do you tell her?
With that broken
9 times 3 times 1 times 3 times. Just boy, what do you?
Multiply 9AB times 3. Oh no, it won't work because they're gonna do lowercase. I'd have to type it in. Okay? Alright? Does this make sense? You love this, right? Everyone loves this. Okay. May I erase this?
I'm tied.
Okay.
Toes.
Thanks.
We're doing
I'm
that.
never saying an H again.
Human beings. We're all just human beings. Yeah. We're all in this together, right? You know what? Today was strange. It was a little humid outside. Yeah.
It was a little
Okay. So, first new topic. Beyond Mendel.
Oh,
Okay?
question.
Yeah.
Why are you wearing a tie?
I don't know. It just felt right. Well, so yesterday, so I told you it was my brother-in-law's birthday over the weekend, and my brother-in-law and I are both elders at our church. And so,
Elders.
yeah. Was that weird because I'm not old?
Yeah, he is, yeah.
I mean,
You're in your 30s,
No,
right?
there's no biblical requirement for age to be an elder.
So I could be an elder.
No, there is a biblical requirement for, yeah, for your what particular stage of life you're in,
Oh, okay.
and for your gender.
Gotcha.
But yeah, anyways,
So you're
so,
elders.
so and he was preaching yesterday, so he dressed up real nice and had like a nice sport coat, so I did the same, and then I was like, man, this is kind of nice. I think I'm gonna do it again. But I didn't put my sport coat on, you know, just
I hate dressing up.
yeah. Every now and again, you can't do it every day because
Feel
then
good.
yeah.
Got a nice fit.
All right, so we need to do beyond Mendel.
I like sweats.
Okay, because we're like, okay, this seems simple enough if we have 2 traits and one is dominant to the other. But what if we have more than 2 traits?
I don't know, man.
I don't know.
Sounds like
man. We have what's called multiple allelism.
Oh no.
I kind of love that.
Multiple allelism, or you can say, sometimes you call this multiple alleles or multiple allelic situations.
What chapter is this?
This is still 14, but I prefer multiple allelism. And then look at this. Basically, this just says some characters have more than 2 alleles. What's wrong?
Av.
Oh, I see what you did now. Okay. Have more than, man, I just started something really bad. Some characters have more than 2 traits. Okay? And so you can have situations like if we have more than 2 traits, we can't just do capital A lowercase a, because then what do we do for the third? So what we'll do is this. We'll do A1, A2, A3, A4,
What is this?
etc. Because we've got multiple alleles for the same trait. And now sometimes it works out nicely that it's like A1 is dominant to A2, which is dominant to A3, which is dominant to A4, right? That's what I mean by greater than. Because if it's greater than, it has to be dominant, right? How else could you interpret greater than? You're like, oh, it could be that there's more of them. Yeah, but who cares?
Yeah, I don't know.
Mark.
I have this would be like a hypothetical question.
Okay, love it.
It's like although it's also sort of off topic.
Okay.
Like in memory of Emily.
Okay.
So what if instead of taking making all the H's silent, what if you make every single one of them like basically
When they're
sound?
supposed to be silent, you sound them out.
Like Howard.
Like Howard.
Or like Connor.
Dwight Howard.
Hunter.
Connor.
I like it. Or Hola.
Oh.
Basically, every H is silent in Spanish. You just you pronounce all those things.
Boys.
Alright? Okay. Shh. Does this make sense? So this complicates it a little bit. What Mendel found out studying pea plants was basically in all these different characters he studied, there were only 2 versions of it. Even with height. Height, it was tall and short. There was nothing in between. It was beautiful. Human genetics isn't that simple. Human genetics, almost all of them are this situation, and on top of this situation, multiple genes for a single character. Like human height, it's not a single gene. It's multiple genes, plus your environment.
Really?
So,
What
yeah.
kind of environment should I be in to be tall?
I mean, one where you're given a proper diet. Yeah.
Wait, is there actually ways to make yourself grow?
Within limits, yeah.
It's like if I was like 6'3",
Okay.
that'd be great.
Any question?
I definitely need to go somewhere.
Alright, goodbye.
Shut up.
Okay, so that's one.
6'3".
Shh. That's one area beyond Mendel. Another one. Codominance. Check this out. In codominance, 2 traits are expressed at the same time. 2 traits are expressed at the same time.
Oh, is that what makes do they like combine or like are they both present?
The best example, I'll answer your question with the best example you can find of codominance. Blood type. A and B blood type.
Okay, but like
A spotted dog.
is it stripes or like does it mix?
It depends. You're thinking you want to try to find another character. It's hard to find good examples of this. It's hard to find good examples of this. They definitely don't mix. Both have to be very obvious.
Okay.
And so like with an AB, if you are blood type AB, you are expressing both the A sugar and the B sugar on your red blood cells. You're expressing both. You're not expressing a mixture of the two. You're expressing both. Both are there. Because we have another type of things where you actually do get a mix. Isa.
What blood type are you and how do you find out what blood type?
You test your blood using antibodies against the particular sugars. No, you just need a drop of it.
What are you?
You just put a little. Why do you want to know my blood type?
Isn't there like only 5 of them, right?
So there's A positive, A negative,
Oh, what?
B positive, B negative,
What comes
O
A
positive, O negative, AB positive, AB negative.
So
There are
there's
8.
What's the most common?
O positive, by far.
Did you say?
It's like
I don't know what I am.
40% of,
We
I
have
think.
a lab where we test our blood type.
Sure.
Wait,
Let's just.
It's
you gotta
gotta
be
be trick
really
your
cool.
finger.
we gotta.
Yeah.
Yeah.
We should do that on Friday instead of the cell growth lab.
Yeah, we should do both.
Definitely
Definitely
not
not
Plus,
that.
it's
Oh, isn't that what the
My baby
people
saw
when you have
cancer.
diabetes? You like have the you like prick
Lancet to prick your
Then you
finger.
put your
Yeah.
blood on the thing and
Yeah.
then you
Oh yeah.
wearing off.
Yep.
My grandma
Okay.
does that every day. She
Yeah.
So is codominance like the flowers that have 2 different colors? Like it's like
Yeah.
purple in the middle and then white on
That,
the
it could be that way. Shh. So Carrie asked, is another example of codominance flowers that are expressing multiple colors? And the answer to that is sometimes.
Oh my god. Like,
Sometimes.
What is this?
Okay,
What is this?
so if this, here's an example of blood type. I don't know why, but we use I raised to the A and I raised to the B to represent blood type. And so this individual here would have type A blood, which happens to be my blood type. I'm A negative. In case you like, if I need a blood transfusion and you also have A negative blood, I will happily accept. Yeah,
Is
Karen.
it A positive or A negative? Like,
There's a second factor called the RH factor. If it's present, it's positive. If it's absent, it's negative. Yeah, this is the second G. Okay, so this individual, wow, that's an ugly A. This individual would have type A blood. This individual would have type AB blood. Both would be expressed. And then check this out. This individual, this is O. Both A and B are dominant to O. This individual would also have type A blood.
that's an
Wait,
O.
then how do most people have?
It's an excellent question because it is a recessive trait. There's just a lot of copies of that allele,
How does that?
even though it's recessive. It's an excellent question. I don't know. I'm not familiar with the studies done on the origins of blood type and when it happened. I know some people groups have more than just those 8 blood types. There's some people groups that have novel blood types, and the idea there is it was a mutation that led to a new sugar being added on the red blood cell surface. Okay, so this is codominance. 2 traits expressed at the same time. Questions? Okay. The next one, beyond Mendel. Man, is it really 9:35? Oh my gosh, or 8:35? 8:35. Next one, incomplete dominance.
is this blending?
This is blending. Yep. 2 traits blend.
Hey!
Hey!
Yeah, it must be money.
So here 2 traits blend.
Yeah, must be the honey.
Check this out. Capital A equals red. Lowercase a equals white. Capital A, lowercase a equals pink.
Ooh, I love
It's a blend. It is a blend of the 2. And you're like, oh, Dr. Engel, this is evidence in support of blended inheritance. Anyone look at this and say, Dr. Engel, this is evidence in support of blended inheritance.
Dr. Engel, it's obvious to support.
They do blend.
Wait,
However, so let's say we did a cross between a female that was capital A, and we crossed that female with a male who is lowercase a. How many different gametes can this female make? Only one type. All of her gametes are going to have the capital A. What about the male? All of his gametes are going to have the lowercase a. So when we do a cross, it's very simple. We have capital A and we have lowercase a. 100% of their offspring are going to have this genotype. Capital A, lowercase a. 100% of their offspring are going to have what phenotype? Pink. Right? 100% are going to have pink. Now if we do, this is F1, remember?
Yes.
What about if we go to F2 and we do a monohybrid cross? Now both the red and the white are going to show back up. They didn't get blended out. So blended inheritance would be once we blend these, they're blended out, right? They shouldn't return. But we know if we cross these, if we do a monohybrid cross, we're going to get the red and the white phenotype back. So they're not blending out. They are blending in that F1 generation, but they're not blending out. They're going to return. Isa.
I'm confused. What is red, white, pink?
Wait. This would be, so a good example of this is in snapdragons. It's a type of flower.
Okay.
And so if it's got two versions of the dominant trait, it's a red flower. If it has two versions of the recessive trait, it's a white flower. And then if it's heterozygous, it's a pink flower.
So what if they're both dominant?
What do you mean?
Like the male and female.
Oh, if they both had capital A, then all of the offspring are going to be red.
Okay, but like. Okay.
Because this is the only way to get the pink, to be a heterozygous. The only way to get the pink is to make a monohybrid individual. If you have this, that's always going to be red. This is always going to be white. This is always going to be pink. Trinity, you had a question? Never mind.
Oh yeah, I know this.
Yeah.
So if they had off like the double A, the double capital A, and the double lowercase a, so if they had like, you know, so when you like combine them together, they were 100% like the same, whatever.
Yeah, 100% of their offspring are going to be pink. If you cross the two true breeders. Okay. All right. We have one more beyond Mendel. You ready?
I'm ready.
Okay.
I'm ready.
This one has a fun name. Epistasis. Last one beyond Mendel that we're going to talk about. It's not the last one beyond Mendel, but it's the last one we're going to talk about.
Epistasis.
Epistasis. And this is basically this phenomenon here. The expression of one gene masks the expression of a second gene.
So is that literally just like normal?
I'm going to show you. I'm going to show you the best example of epistasis.
You're not Dr. Phillips.
No, but he's back there.
Oh, okay.
Yeah.
He doesn't
Yeah.
eat coffee.
You really don't.
No one should give him coffee.
Okay, so the expression of one gene masks the expression of a second gene. Let me show you the best example ever. Okay? Best example literally ever. Okay, so we have one gene called the BB gene. Okay? And what it codes for is pigment type in Labradors.
Oh, I love
I
Labrador.
thought he was
So capital B is giving us the black pigment to make ourselves a nice black Labrador.
Hold up.
The lowercase b is giving ourselves the brown pigment to make ourselves the chocolate's the brown one, right?
The chocolate.
Chocolate lab is the brown one, and then the black lab is the black lab.
So that would make sense.
Yeah.
I have a story.
Except for white.
It's not a story, it's just a little thing, a little bit, a little tidbit. Yesterday I went to my friend's house, Oh my gosh, I saw the cutest dog. And guess how much it weighs? Less than a pound.
It's like one of those dogs that like fits like right
So cute. It
Put
was
it in your
it was a teacup Yorkie.
Oh.
And it had a car seat. So
Okay. So we've got. We have one character. Capital B gives us a black color. Lowercase b gives us a brown color.
What about yellow?
But black is dominant to brown. So this BB would actually give us a black lab. Okay? So capital B is dominant to lowercase b. So capital B, lowercase b is going to give us a black lab. Capital B will give us a black lab. The only way to get a chocolate lab is to be what?
Lower B, lower.
Lowercase b, lowercase b. But here's the deal. You're like, that's not epistasis. That's normal Mendelian inheritance. You're right. We have a second gene called the E gene. And this capital E is yes pigment. Lowercase e, what do you think it is? No pigment.
What? How does that work?
No pigment. You can't deposit the pigment. It doesn't matter what color it is. You can't deposit it. And so if you get no pigment, you get the blonde lab or the yellow lab.
That's kind of
Yellow lab. And so if you've got lowercase e, you are a homozygous recessive individual at this gene here, you do not deposit pigment. It doesn't matter what you are here, because it doesn't matter what pigment you're making, you're not depositing it. You're always going to be a yellow lab. Always going to be a yellow lab. Okay? So this is one of the things on Wednesday when I said we'll have some fun with inheritance. We'll cross two Labradors and you'll predict what their puppies are going to look like.
We're gonna breed.
No, we're gonna breed.
Yeah, we're going to breed Labradors on Wednesday. And we're going to accelerate the gestation period from the normal 60 days
2 minutes.
to about 20 minutes. 2 minutes, that's impossible. We'll accelerate it to 20 minutes. Okay? Does this make sense? So here we have the expression of one gene masking the expression of another. Because if you don't deposit any pigment, it doesn't matter if you're supposed to be a black lab, you're going to be a yellow lab.
So yes, pigment is dominant.
Yes. All you need is one copy of capital E and you will deposit pigment. And then you're either going to be a black lab or a chocolate lab, a brown lab. Okay?
So theoretically, most of them should be black.
Yes. Uh-huh. You bet. Truly. Truly that is true. Now if you cross two yellow labs, you know both those individuals had
So it has to
lowercase e,
be
lowercase e, they're always going to produce yellow labs. But if you cross a yellow lab with like a brown or a black lab, and you don't know what if they were this, or if they had two capital E's, then you can get all of the different colors to show up.
This is just a whole mixture.
The possibilities are almost endless. We only have 3 different phenotypes. Okay?
We'll create more.
Any questions on Beyond Mendel? Okay. Goodbye.
Are we done with chapter 14?
We are done with chapter 14.
That was fun.
And you're like, Dr. Engel, you told us we were going to get all the way through 15.
You're done with chapter 14?
Yeah.
You still don't know the name of this chapter?
I don't. I'm sorry. Okay. Okay, so we're going to go back. We're going to talk about meiosis. And we're now going to use meiosis to explain Mendel's laws. And this is how chapter 15 starts. Okay. I don't. I'm sorry. I need to write these down so because I know you're always.
I put unknown for chapter 14.
Okay, so here's our cell. Here is our cell that is going to begin meiosis. This is a germ cell. Now, germ cells will either develop into sperm if the germ cells are in a male mammal, or a male animal in general, it doesn't matter whether it's a mammal or not, or they will develop into ova if it is in a female animal, okay, or a female plant.
Wait, what's the title of this?
How's your response?
I don't know. I'm sorry. The title of this chapter is chapter 15.
No. Can you just like get overall about what the chapter's about so I can just name it?
Chapter 15 is probably called something like chromosomes and inheritance. Chromosomes and inheritance. And chapter 14 is probably called something along the lines of Mendel and inheritance.
You said 14 was
Mendel
inheritance.
Or just inheritance in general? Okay.
Unknown.
Alright, check this out. You ready for this?
Maybe.
Okay, you are. Okay, can you see that we have 2 different chromosomes in this germ cell?
Yeah.
No. Oh yeah,
2 different chromosomes, and why do we have 4?
2 of each.
Because you have 2 copies of each chromosome, one that came from mom and one that came from dad, yes? Alright, now let's look at this.
Is it on purpose that one's smaller than the other?
Yes,
Oh.
yep. That's how you can tell they're 2 different chromosomes.
Let me fix it.
It is on purpose.
I can't read with.
Oh, you can read it.
Oh, that's capital A.
Capital A on one version of this chromosome, lowercase a on the other version of this chromosome, capital B on this version of the chromosome, lowercase b on this version of the chromosome. So if we were to write the genotype of this individual, what would it be? The genotype. This individual would be capital A, lowercase a, capital B, lowercase b. What might we call this individual? We might be tempted to call this individual a dihybrid because it is heterozygous at both genes, or for both characters. Love it, Lydia. Nicely done. Okay, but why does this individual have 2 copies of capital A and 2 copies of lowercase a? What do we call these, Rick? You were the one that brought this up. You were the one that...
Chromatids.
Sister chromatids.
Sister chromatids.
Because what has to happen before we begin meiosis?
They need to
We copy the DNA. And the 2 identical copies are physically attached together as, Rick?
sister
chromatids. Okay? Now, meiosis happens in 2 cycles. We've got meiosis 1 and we have meiosis 2. So let's do meiosis 1.
I was here for this one. This is where things get fun.
After meiosis 1, we have 2 cells. Okay? Do you see what happened there?
Yeah, all the 2 dominant ones.
Yeah?
No way. And they split them together.
And then over here we've got look at that! After meiosis 1, because during meiosis 1, you know that the homologous chromosomes separate from each other, right? We don't pull the chromatids apart,
Not yet.
we pull the homologous chromosomes apart.
Why are the A's big and the B's small?
Over here both are capital, over here both are, oh, you mean the chromosomes?
Yeah.
Because they're different chromosomes. Yeah, they're different chromosomes. And that's how it works in our cells as well. Chromosome 1 is the largest of our chromosomes, all the way down to chromosome 22 is the smallest when it's in its condensed form. Yeah, Kate.
Why isn't it big A with little b?
That's an excellent question. So this is one option of what could happen, right? But it could have also gone the other way. Remember when we talked about how does meiosis increase diversity? And we said, well, they could be... this could have gone the other way. That excellent question. So this could be this, or It could have been this.
Oh my lord. I got two little bees.
Little bees.
Ah.
I want to write that.
Yep. Sure do.
How would you not want to write it, Trinity?
Okay? So either of those options are possible, right? And now during meiosis 2, ooh. This is going to be meiosis 2. So of course this over here.
What? I don't have room for those arrows.
Oh, you have room.
Well, you can go straight down if you want.
No.
You can just press it.
You have room.
Make room. You can do it.
Oh.
Oh my
On the
gee.
side of the paper.
Holy Lord.
I mean, the shape of the board should indicate to you how you're. Listen.
Should I do it
Listen, we've been doing this for several months now. You know I make full use of the board. So by this point, you should probably turn your notes sideways so that the shape of your paper is close to the shape of the board.
That's not the way the lines
go.
It isn't the way the lines go, you're right. But see, you make your paper
Off-road.
what you want it to be. You're in charge of your paper's
You
destiny.
need more the lines of your paper.
The line.
I'll make new lines.
Okay,
Oh, I thought he said
Make new lines.
line. I was like, what lines are we talking about?
okay.
Show me.
So now after meiosis 2, we split the sister chromatids apart.
Would that mean there's 4, technically?
Yep. You bet. There are always 4 cells at the end of meiosis. When you complete meiosis, you started with 1 cell and you end with 4.
What are those crosses?
Crosses.
Yeah,
Those are the sister chromatids.
Oh.
Got split.
Oh.
Yeah, they've now been split during meiosis 2.
Oh, those are sister chromatids?
Well, not anymore.
What are they?
They were sister chromatids when they were attached together, but once they're separated, they're not sisters anymore.
Oh, that's wrong.
I know. I know.
My sisters.
Bye-bye. Bye-bye now.
We got the meds.
Now, they may be reunited at some point and become sisters again.
What are the sisters?
Oh, I need to tell you a story.
Oh, yes, please.
We love story time.
Okay?
Story times with Mingle.
Yeah. And so there's meiosis 2. And so we basically get these 4 gametes, or these 4 gametes. And look now, the segregation of one gene, the A gene, did not influence the segregation of the B gene, right? Because we could get either of these. We can get the 2 capitals staying together, or we could get one of the capitals and one of the lowercase, right? Right? Yeah! The law of independent assortment. And not only did we use meiosis to show how the law of independent assortment works, but we also used meiosis to show how the law of segregation works. Because the 2 forms of A segregated from each other, and each gamete only gets one of them, either the capital or the lowercase. Right? So there's how both the law of segregation and how the law of independent assortment works. Okay? We're going to take ourselves a little bit of a break, and I'm going to tell you a story. Yes.
Finals week.
December.
Okay, look at this. Look at this. Okay, we're going to do this again. But now, shh. Shh. Check out this situation here.
Vital situation.
Bob off.
I really don't want to draw this.
You do want to draw this again, Kyle.
We're drawing it again.
It's a different one though.
Doesn't get any better than this.
Doesn't
Doesn't get any better.
Look at this. Now we have just a single chromosome set, but we still have two of them, one from mom and one from dad. What would this individual's genotype be?
Oh, wait, can you say what genotype is again?
Genotype is the actual
Oh, okay.
what traits do you have the code for, not what traits are you expressing. This individual would still be capital A, lowercase a, capital B, lowercase b, but what's the difference? Somebody tell me the difference. Katie.
That it only has 2 instead of 4.
They're on the same chromosome, right?
Whoa!
The two characters, the genes for those characters are on the same chromosome.
That's weird.
That is weird.
Whoa.
So after meiosis 1,
Are they gonna like split the chromosome?
just relax.
Yes.
So after meiosis 1, when we split our homologous chromosomes, okay, so after meiosis 1, we have these two cells. Is there an OR in this one?
There is not.
So what you're saying then is they are not going to assort independently if they are on the same chromosome.
Oh no.
We don't have a mechanism by which we can switch material on chromosomes where you can actually create a chromosome that is part your mom and part your dad.
That's
Yeah,
called
that's-
Crossing over. So we still have an OR. Check this out,
Okay, I
everyone.
didn't look at the board.
Everybody, look at this.
It's right there, right? It's in your blood, right?
Oh.
Yeah. Right. Yeah.
Oh, now there's an OR. Oh lordy.
Wait, that's the thing.
He has the
Huh?
correct set of genes.
There's a lowercase b in there.
Wait, where is the crossing over?
Oh,
I see.
Oh my god,
What?
that's really disturbing. What's your guys' favorite moment? I like the potato.
Potato.
Look at that.
Slaps, right?
Give me like.
Potato one.
We had a crossing over.
Yeah, the potato.
Stab
it with your pencil.
Do we have any more ORs?
Yeah.
Yes, we could have had a completely different kind of crossing over.
Oh my.
Look at this. Look at this.
Kyle, this is so funny.
This it's so funny. Check that out. We could have had this situation with yeah.
Again.
Check that out.
Whoa.
We could have crossed over at a different position on the chromosome.
Whoa.
It's like magic. No.
Is there any more ORs?
I need an infinite amount.
Well, there is, but it would accomplish the same thing.
Not worth right now.
And so, what I want you to see is because of crossing over, you need to write this. I'm not going to go and do the rest of meiosis 2. But because of crossing over, even if the two genes are on the same chromosome, they will often still assort independently.
That's weird.
It is weird.
Hey, the beard is weird.
The beard is weird.
Okay, because of crossing over, so you wrote crossing over here and it's right next to these different cells where you're drawing OR, so you're like, oh, that's right. Crossing over creates chromosomes that never existed before. To where I have chromosomes that are part my mom and part my dad. You're like, this is so cool. What would a combination of my mom and my dad be? And you're like, this chromosome right here.
Wow.
Because of crossing over, they can still assort independently. Okay, because of crossing over, independent assortment still works. Another way that we are using meiosis to demonstrate Mendel's law of independent assortment. That the segregation of one character does not influence the segregation of another. Okay? We're not going to do meiosis 2. I just want you to get to this point and you're like, that's right, crossing over. Alright? Any questions? You love it, right?
Yep.
Okay. We have to like sum all this up now.
Thank you.
Bless you.
Thank you.
You're welcome. Okay, we gotta sum all this up. You ready for that? May I erase this?
Yes.
You may.
Okay, cool. I should get somebody to draw for me, because
Yes.
Yeah, you really should.
Definitely. We've messed up.
you know, I haven't made a mistake in a while. I made that mistake and then had to pay up on it, but I haven't made one in a while. I'm feeling like we should make another agreement here.
I definitely should.
Oh, yeah, that calm down.
I definitely should. So.
I don't know. I'm feeling pretty like I'm feeling pretty jazzed this morning. So today might not be the best day to make this agreement.
We should make this agreement right now.
Okay. Okay, I want you to redraw.
Wait, look, that's female, right?
Yep. Yep. I feel like we might be at the point now where I just need to like shut off all fun things. Like no more snacks in class, because that's a rule.
Yeah.
Is it?
What?
Like,
I don't know what you're talking about.
I've never had
like, can I give demerits? Do you all have demerits?
No.
Can I take house points away for you behaving poorly in class?
This is Cincinnati.
Give us attention.
I totally can
You
I?
can give detention too.
But and I can take house points away. Can I take house points away?
I think we
You
could
definitely
spend anything we want. Yeah.
Oh man!
Hey, Cincinnati's already lost.
We have nothing to lose.
Can I award house points for like really good behavior?
Amy's got it all. Yeah.
Yes, what do you got?
All the points we
Hey, where are we at with the whole corporate time?
Hey, we can do things sometimes.
I don't know if it's in the
They did share a Google Doc. Yeah, she shared it with me.
Oh yeah.
But as far as
I don't think I've seen it.
What are we doing? Oh,
did she just share it with me or did she share it with everyone in the class?
I didn't check. But she
I checked my Google Docs.
It's shared with you.
It is shared with you. Okay, so she should.
I saw that.
But she said that
Because we're doing some Backstreet Boys song,
But
right?
then she's talking about she said that it was pretty boring and basic. So that we should go to St. Caroline. She said she was doing this training about
Oh my gosh.
So I don't know.
You know what?
Maybe she confused them.
Corporate time is next Friday, right?
What? No, it's not.
Wait, really?
No, I
Yeah.
think it's.
We should
It's
definitely
March
work
8th.
on that. That's when our heart games is, right?
No.
Isn't corporate time on March 8th?
I really don't know.
Because this Friday's March 1st.
Did I never tell
Which would make next Friday March 8th.
March 8th is corporate time.
Yeah, and this beautiful thing is I don't teach that day, so I won't even be here to like be embarrassed by what happens.
You have no
Okay.
faith in us.
You need to.
IMAX.
Yeah.
You have no faith in us.
Okay, so check this out. So this female, her genotype would still be capital A, lowercase a, capital B, lowercase b, yes?
Yep.
Alright, so that's still her genotype. We're going back to the situation where we said crossing over will ensure that these sort independently of one another. Okay? So which means this female should be able to make 4 different types of gametes. She should be able to make one that's got capital A, capital B. She should be able to make one that has lowercase a, lowercase b. Right?
Big B.
She should be able to make one that's lowercase a, big B.
Sir.
And she should be able to make one that's big A, little b.
Little B.
Okay? right? She should be able to make these 4 types of gametes. Do you agree?
Yes.
If they're sorting independently. What percentage of the gametes should be this one?
25.
25%. What about this one?
25.
25%.
Wait, even though they're all lowercase?
What about this one?
Will they like make up?
Well, because we're not crossing yet. You're getting into like phenotypic ratios. We're just making gametes right now. Okay? We're just making gametes. There's something really great happening here, Rick, and you're missing it. And losing points for Cincinnatus.
Hey!
Okay. So these two. I need to talk. Who's in charge of all of the houses? Is it Mr. Lee?
No.
I'm gonna talk to him about what I'm capable of doing. Is he also a leader for one of the houses, or is he just over everything?
He's unbiased.
Yeah, I want to know what I'm.
What teacher do you talk to?
I talk to Mrs. Parsons every day that I come in. I talk to Mr. Margrave every day.
Just the name.
Because they're down here, it's convenient. I don't really go hunting for people. I usually talk to Mrs. Carty because she's around.
She's sweet.
Yeah, and so I'll usually talk to her. Who else do I talk to? I talk to Mr. Weichbrot often because he's usually roaming around, and I'll see him. And
He's a cool guy.
yeah. And then I talk to.
He's a true renaissance.
It's Mr. Culp.
Yeah.
Yeah, I know he's not a teacher. Oh, he does teach. He teaches government, or yeah, one semester. So I talked to him. Okay, shh. So check this out. This was the female cells. Every cell in her body looks like this. So from one of her parents, she got capital A, capital B, yes?
Yeah.
And from one of her parents, she got lowercase a, lowercase b. So we call these two gametes, we call these parental gametes. Because she's basically making gametes that have chromosomes unchanged from the ones she got from her mom and dad. Does that make sense? So these gametes are making chromosomes that basically were the same as the chromosomes that fused to form her. Right? So we call these parental gametes. What do you think we call these? What's another name for crossing over?
Moving.
Do you remember this? You're never gonna get this. I'll just give it to you.
Recombination.
Recombinant. Recombination is another name for crossing over. Is recombination.
See, boom.
So we call these recombinant chromosomes or recombinant gametes, and these are parental gametes. These are recombinant gametes. Check this out. We have a nice if they assort independently. If they assort independently. I'm going to abbreviate that because I don't want to write the whole thing out. If they assort independently, the number of recombinant over the total gametes. The marker freaked out. The number of recombinant divided by the total number of gametes should equal what?
1.
What?
It shouldn't be 1.
25%.
Well, they're two. Yes.
1/4.
0.5. 1/4. That's for each type of recombinant. This is the number of recombinants total. Rick?
Sorry.
Take points.
But you said the same thing. And you're in the same house.
He deserves it.
I'm okay with you taking points away from Cincinnatus because we're going to lose anyways. But I just want you to make note
Come on now.
that it was from Rick.
Wait,
No, no, I was being Carrie in that moment. Could you not tell?
No. Dr. Engel, do you have a house?
No.
You definitely should.
They don't give.
Hey,
They
you're
don't-
red. You're red.
He definitely should go
Good
to
red,
Cincinnatus.
Cincinnatus.
They don't give houses to part-time people.
They should.
Okay, but what house do you want to be in?
Dante's the right answer.
No, it's not. Dante. The only reason Dante is
Dante's smoking it right
is
now, right?
because Mrs. Cat is
Actually,
always
I
girl.
love Patrick Hurley.
Actually, it's not.
Facts.
Thank you, Dr.
Let's see, it's It's Boethius, Dante, Cincinnatus, and Patrick. The irrelevant. Mark.
Like for some reason, when it comes to teachers, like every single one of them gives me some sort of house vibe. It's sort of it's like out of all the like basically I look at them and sort of like, okay, this is what house they're in. It's sort of like, and for some reason you're giving me like a Patrick vibe. I don't know.
No.
Somebody just called Patrick irrelevant. And then
To me, they're not irrelevant.
now, first of all, the houses shouldn't be named after the houses in Harry Potter. That's the first thing.
They're not.
Right? They should be. They should be.
I didn't even watch Harry Potter.
And I'm a Hufflepuff.
Oh, same.
I only know Gryffindor.
Are you a Hufflepuff?
I'm Southern.
You would be. All right. Okay. Katie.
Can you? I forgot what assorting independently means. Could you point
Look,
to the
actually,
word
the thing got me was the.
Whoa!
Okay.
Oh, it's the law. It's the law. Never mind. I got it.
So Katie asked for a reminder of what assort independently means, and it's the law of independent assortment. That the separation of traits for one gene does not influence the separation of traits for another. Okay? So if they assort independently, the number of recombinants over the total number of gametes should be 0.5. If it is anything less than 0.5, it is telling you that they are not sorting independently.
But
Wait, how could they not sort independently? It's a lot.
What if they're really close together on the same chromosome?
Laws are
can it
suggestions.
mutate?
Okay, you had a second question though, right?
That was my second question. We're good.
Okay. So if they assort independently, the number of recombinants over the total number of gametes should be 0.5. If that ratio is anything less than 0.5, it tells us that they are not sorting independently. So what I'm going to write is down here, if it is less than 0.5, okay, this value here, let's put a little asterisk. No, not right there. Anyways, I'm not even going to mark it. So if this is less than 0.5, we call this genetic linkage. And what that means is that the genes are actually linked together. They're close enough together on the same chromosome that they're not always being mixed up by crossing over. They're linked. Linkage.
What?
They're linked. And so now I told you chi-squared was going to make a return. Oh yeah. Oh yeah. Okay, so if it's anything less than 0.5, they're linked. And now the question is that difference significant or not? And chi-squared gives us the tool by which we can answer that question. So let's check this out. Okay, can I erase this? May I erase this? I know I'm physically capable of erasing it.
You may.
Thank you.
Okay.
It's your passion. You can do what you
Yeah, but it's your education, so I can do what I want within limits.
I have a rainbow turtle.
Okay, so check this out. Okay, check this out. Hey, you cross Drosophila, right? Those fruit flies, and this time you do it in such a way that it actually works.
Don't kill him.
Okay? You do it in such a way that it actually works. And let's say they form 10,000 offspring. Yeah. Yeah, 10,000 offspring. 2,900 have this chromosome here. This is going back to our previous example, right, where capital A, capital B, and lowercase a, lowercase b are both parental. Okay? 3,100. Whoa, not 31,000. 3,100 are this. Okay? I guess you'd have to do gametes and not, anyways. So this together is 6,000, right? Is that right?
Yeah.
2,100 are this. And 1,900 are this. Wait, there we go. Had to get my letters right. Okay, these two right here are parental. Yes, from our previous example. These two here are recombinants. And now we need to determine our recombinant over our total. What ratio is that? Okay, so our number of recombinants goes on top.
It'll be 40%.
It will be 40%, but we represent it not as a percentage, Rick, but as a proportion. So we get, well, it's actually 4,000 over 10,000.
Where'd you get 4,000?
Can we
Oh,
simplify
never mind. I got it.
We are going to simplify this, and it's going to give us 0.4. And we said anything less than 0.5 is an indication that they are linked. That linkage is going on. Yeah, Karen.
If it's greater than 0.5.
If it's greater than 0.5, it's like that you can almost guarantee is going to be a statistical anomaly because you. Hey!
Your hair looks so good.
Thank you.
Thank
Who are
you.
you trying to impress?
Myself.
Welcome.
Thank you.
That's so cute.
All right, everyone. All right, everyone. Hey, you know what? I discovered today, tentatively, that I may be capable of taking house points away from people.
So basically,
Do you have a house?
I don't have a house, but there's some people in here that are having
Tori will
a.
be here soon.
There are people in here that are having a hard time staying focused, and I'm thinking about maybe taking some house points away.
Why'd you?
All right. Okay, so this is an indication that they are linked. However, true or false, this could be some statistical anomaly.
that's true.
It could be what?
It's true until proven otherwise. We need some tool by which we can say this is not some statistical anomaly. And what statistical tool do we have? Chi-squared. Chi-squared is making a return. Oh, here, we'll go over here. Check this out. Check this out. Are you ready?
So ready.
Okay, you're so ready. So we have. We have our expected table. Okay? Our expected table. And we have our observed table. Do you remember doing this with chi-squared? Oh, you do.
Of course.
And you love it. Okay. So what are our expected values? What are our expected values?
Is this for the same thing?
So these are our gametes that we actually produced.
We expect
25% of each, right?
Yeah, so 2,500.
Hey, shh, everyone. Everyone, something important's happening.
I don't know what's going on.
I was putting production. Aren't you to the
Yeah, but you can get we have it all recorded.
And I'm just trying to figure out where we're at.
Okay, so our expected values were 2,500 for each.
Oh, yes.
Because if they were assorting independently, 25% of gametes should have had this condition, 25% of gametes should have had this condition, 25% of gametes should have had this condition, so on and so forth. But that's not what we got. Here are our observed values. 2,900, 3,100, 2,100, and 1,900.
Where did we get this 25?
Where did I get that? That's what they should be. That's what we expected. Because 25% should be each of those chromosome types, right? We had that up on the board. Does that make sense?
Yeah.
And there are 10,000 total, so 25% of 10,000 is 2,500. Now somebody remind me how we calculate chi-squared.
Carrie just said.
Yeah.
Okay. So it's expected. Oh well, the sum of expected.
No, it's observed minus expected squared.
Observed minus expected.
Observed minus expected.
Yeah.
Observed minus.
Let's
Right?
Yeah, observed minus expected
Squared.
divided by expected.
I knew it was expected on the bottom. That's why I thought it was.
I just remember the top, the right in the bottom.
This one
So that's how I got that.
I knew they expected.
squared here
Hey,
divided by
Cincinnati's house points be on the come up.
expected.
Yes.
Yeah, that's it. Yeah.
Okay? Observed minus expected squared divided by expected. That's our chi-squared value. Okay? It's the sum of our observed minus expected quantity squared divided by expected. So let's do this. 2,500 is our observed is 2,900
So 1,600.
minus 2,500
1,600.
quantity squared divided by 2,500. Yes?
60,000. Sorry. Wait.
And then we gotta add
400 squared is
3,100
4 zeros.
minus 2,500 quantity squared divided by 2,500. Okay? Yes? And then we gotta add in our next one. 2,100 minus 2,500 squared divided by 2,500 plus, what's the last one? 1,900 minus 2,500 squared divided by 2,500.
that for each one.
Oh yeah.
And we have to write each one down.
Yeah, and we gotta calculate these. Okay? Shh. So 2,900 minus 2,500 is 400.
Squared.
And Rick, what is 400 squared? You said 1,600, but it's
No,
not. It's
It's
16,000.
16 with 4 zeros.
The answer is 64
16 with 4 zeros.
for the first part. First one.
This one alone is 64.
2 zeros on
That's
each.
64.
Okay. All right, and then we gotta get the rest of them.
Common core, right?
160.
Right, it's common core.
Common core, exactly.
64.
I was educated in Common Core.
Oh, 160,000.
It's K for.
The next one's 144.
I like
Alright,
those.
Oh man, check this out. You know what chi-squared's gonna equal?
What?
416.
That was supposed to be.
You can keep working it out, but it's gonna be 416. Nope. Nope. Yes. No. Yes.
Check your math.
Yeah, it is. So chi-squared is 416. That is a massive chi-squared value. Somebody pull out your sheet that you have for when we take exams.
Oh, I have it. No, I'm gonna get mine first.
Okay, Emma's got
That's not it.
Okay. So here. Let's see. Let's check this out.
Do you make copies of that?
Okay. So we have. Yeah, I'll get some more. I'll make sure when we take another. Okay. So the number of degrees of freedom for a chi-squared analysis is the number of rows minus 1 times the number of columns minus 1. Okay, but the fewest number of degrees of freedom you can have is 1. So this is going to be the number of rows is 1 minus 1 is 0. 0 times anything is 0. So this would have 1 degree of freedom. Okay, so for 1 degree of freedom, if we wanted to have basically our p-value of 0.05 says that the probability of getting these results based on randomness alone is 5%. And that's where you draw the line. You say, okay, that's statistically significant. But let's say that's not good enough. We want something less than 1% of a chance that it could happen if they're really not linked. That it's just a statistical anomaly. Okay? So with 1 degree of freedom, the chi-squared value, the significant chi-squared value, to tell us that these data would happen if they aren't really linked, 1% of the time, you know what that chi-squared value is?
416.
6.7.
So close.
True or false? This is greater than 6.7.
Yes.
That
A
is
little bit.
true.
A little bit.
So the probability of getting data like these, if these genes aren't really linked, is probably like 1 in 8 billion.
So,
So what would we say? We're like, these things are linked. These things are linked. They are so close together on the chromosome.
How many zeros?
How many zeros does that have, Rick?
What? 8 billion?
10.
Yeah.
No, 9.
9. And 8 with 9 zeros.
Yeah.
If it was 80 billion, it'd have 10. Okay, does that make sense?
Yeah. That's a lot
So
of
we're like,
steps.
okay,
Neutral steps.
we had a suspicion they were linked because our number of recombinants divided by total was less than 0.5, and now we have a statistical tool that says that we have reason to believe that they are significantly linked, that they are linked together, that these genes, whatever they are so close together on the chromosome that crossing over cannot ensure that they assort independently. Trinity.
What did the 416 have to do with that again?
416?
Yeah.
It's just, this is what our chi-squared value is. That table just tells you your critical chi-squared value. So if this is greater than or equal to that critical value, it tells you that there's 1% or less chance of getting data like this if they aren't really linked.
Wait,
So the smaller the number is, the more.
The smaller the chi-squared value, the more likely it is it could just be a statistical anomaly.
Okay, the higher
But
it is, the more.
the higher it is, the more likely it is that no, they're really linked together. They're really linked together. And the nice thing is this, if you want to know how linked are they? How linked are they? We can give approximate distances between the chromosomes. And all of this work was done and presented, published by a guy named Thomas Morgan. And so we measure the distances between genes in what unit? What do you think? In Morgans. We measure.
I really want to do it in Tom's.
Isn't that wonderful? We measure the distance between genes in Morgans. More commonly, we measure it in centimorgans, which is 1/10 of a Morgan, right? Centi, that root centi, like centimeter. 1/100th, not 1/10. Gosh, that would be deci. But yeah, we measure it in centimorgans.
I like that word.
Isn't that fun?
Yeah, centimeter.
And so this is this is what's so beautiful, and then we're gonna be done. Listen, one more thing that you have to learn today, and that's what a centimorgan is. So 1 centimorgan. This is centimorgan. This is 1 centimorgan.
Look at the centimeter with the bigger end.
1 centimorgan is equal to, you ready for this?
Yeah.
0.01 recombinant frequency.
Whoa.
I'm just gonna say centimeter.
Recombinant frequency. And how do we determine recombinant frequency again? Somebody remind me? We do the number of recombinants divided by the total.
Whoa.
So if 1 centimorgan is 0.01 recombinant frequency, and what did we get as our recombinant frequency, Rick, when we did this? 0.4. So what is how far apart are those two genes from each other? 40 centimorgans.
Whoa! That's kind of nifty.
Is the one that we should have gotten, but we got before.
40 centimeters.
Okay? Is that okay?
Yeah.
Is Tori even gonna come?
She said she was coming. She texted me.
Okay.
No, slide
She's at the doctor's appointment.
Hey, we were talking about dogs earlier today.
Really?
Yeah. And I told everyone, so what we're going to do on Wednesday is we're going to take all these genetic principles and we're going to work real life applications with it. So we are going to simulate a cross between a yellow Labrador and a brown. No, we'll do it between a yellow Labrador and a black Labrador and see all the different combinations.
And we're bringing them in, right?
Can I bring my dog?
We're going to win.
Please.
You can bring a picture of your dog.
Okay, yesterday I was at the park and I saw 2 corgis. And I was wearing corgi socks yesterday too. So it's really nice.
All right.
Corgi.
Okay. So if our recombinant frequency was 0.25, how far apart are those two genes from each other? 25 centimorgans. If our recombinant frequency is at its maximum, which is 0.5, right? That's where it'll reach its maximum. They're at least 50 centimorgans. They could be more, but they have to be at least 50 centimorgans apart. Now, if they're on separate chromosomes, it's very easy to make sure they assort independently. But if they're on the same chromosome, what's the only way to make sure they assort independently? No, not chi-squared. That gives us a statistical tool. But if the two genes are on the same chromosome, what mechanism is the only thing that will ensure that they assort independently? Rick?
I was confident, but I'm not.
Were you gonna say? Were you gonna say crossing over?
I was, yeah.
Yeah, that's exactly the right answer. Crossing over. Now, if they're on separate chromosomes,
That's obvious.
if they're on separate chromosomes, they're always going to assort independently. But if they're on the same chromosome, they will assort independently as long as they are how far apart?
25.
At least 50 centimorgans.
Yeah, because you have 2.5.
Isn't that the max though?
Yeah.
That's the max measurement that you should be able to expect to get. But they can be further apart than that. You just couldn't measure it that way.
Okay.
Yeah. No, that's an excellent point to bring up. Shh. Real quick, everyone. What if you wanted to know exactly how far they were apart and you got 50 centimorgans? Because it could be 50, but it could also be greater than 50. How might would you? What's that? Measured in increments. And what would you look? Shh. You're onto something there. Measured in increments. So what would you look for in between those two genes?
I don't even know
A
what we're talking
third
about.
gene.
A third gene.
What if you could find a third gene in between our two genes? Like, check this out. Watch this. Where's my marker? Oh, it's right there. Check this out. What if we did these calculations and we get that A and B are 50 centimorgans apart? And you're like, okay, they could be more. 50 centimorgans, that's the maximum we can measure.
Right.
But what if you go, I bet there's a gene in between A and B, and let's call this gene, what do we call it?
C.
Let's call it C.
8.1.
C's after B.
What if we find another gene in between these, and then we measure the recombinant frequency between A and C, and then between C and B, and then we can actually get an actual measurement. Well, then you've got to find another gene.
Oh my G, Carrie.